I've shared the slide with you. Okay, before we start, let's recite Umul Kitab Al-Fatihah first. Okay, so where's the... I've shared the slides through WhatsApp in case you want to refer to it. Yeah. And then I will share with you my screen. Oh, let me start the recording first before I forget. Okay, a window, and then this note. What's this one? Okay, so here we go. We got the second lesson. Yeah, second lesson slide, which is DC machinery fundamentals. Yeah. So we are going to look at the fundamentals, yeah, of the theoretical fundamentals, how these machineries are working, especially the generator and motor. Okay, and then we are going to apply some of that we learned in the previous lesson in this lesson, inshallah. Right, and here is the contents. We will try to go through the theory, the explanation how these machines work, and we are going to start with the most simple form of this machine, which is a single loop. Yeah. In real machines, you've got so many loops, yeah, so many windings on the rotor. Yes, to help us understand it gradually, step by step, yeah, we're going to develop or build our understanding. We are going to start from the most simple form of this machinery, which is a single loop. Right after that, we are going to look at a more complex one, but still relatively simple, which is a for loop, yeah, machines. And then after that, then we are going to look at a more realistic machine, inshallah. Following this, then we are going to look at some problems with the mechanism in terms of commutation, especially what are the problems and what are the solutions that have been offered or available for us. And finally, we are going to have a look at the losses in such machineries. Right, okay, but for this lesson today, I think we are not going to cover all of this, probably about a third or half of it, if we can, then that will be good. Yeah. Okay, let's start with the first form of DC or machinery, which is a single loop. Oh, sorry, where are we? Okay, let's go back. Okay, right, yes, as introduction, we are going to develop our understanding on DC machinery fundamentals. And this is going to be achieved by looking at simple machinery, starting with a single rotating loop, yeah, which is illustrated here. Okay, now again, what we have here, we are starting with is a single loop, and that loop is rotating, as we will see later. Yeah. So if you look at the illustration here on the right hand side, yeah, can you see the loop? It's made of piece of wire. Yeah. Okay, which is this one here. Okay, it's a bit too thick, but I will delete it later. Okay, so this is the loop. Yeah, and the loop is wound around a cylindrical core, yeah, ferromagnetic core. Okay, now I'm going to delete my scribble here. Yeah, So can you see the cylindrical core, which is this? Yeah, this is the cylindrical core. Okay, so you've got the loop, which was this, yeah, is wound around this core. Okay. Now, can you imagine how does it look like in reality? Remember, this is a 3D model. Yeah, it's not a 2D model. Yeah. Okay, and again, the cylindrical core, yeah, is made of ferromagnetic material. So now, if you look at from the front side, yeah. Okay, before we go to the front side, and this cylindrical and the single loop is located between two magnetic poles, north and south. Yeah, can you? Okay, so this is north, and that's the south one. So it's located between two magnetic poles. Yeah. Now, if you look at from the front side, how do they look like? Yeah, it's like in the figure B. So the middle part is the rotor, and then it's located between two magnetic poles. Yeah. Okay, sorry. Yeah, which is this and this. Okay, north and south poles. And because they are magnetic, magnetic flux will be produced, and the flow of the flux is as shown in the illustration. Yeah? So they are not going straight. Yeah? I draw it again. I'll just remove the easier like this. Okay, so the flux lines are not straight like this. Yeah? It's not horizontally going like this, but instead it's just like what is shown on figure B. And the reason being that if you look at the explanation here, yeah, the flux lines are trying to find themselves the path with the least reluctance, yeah, the smallest or the lowest reluctance. And when they go through the air gap, the lowest reluctance is the shortest distance in the air gap. Yeah. So I can draw it again. For example, if you have this, yeah, and that's the, okay. Let's just draw it like this. Okay. So if the flux have to go through the gap, it will go through the shortest distance. Oops, sorry. Yeah, the shortest distance. So it's not going to go like this, for example, yeah, because or like this, yeah? But it's going through the shortest distance, connecting the two parts, yeah, the magnetic pole and the core. Yeah, so this will be the shortest, and the shortest is in this case will be perpendicular to the surface of each part. Yeah? So this is going to be perpendicular to this, and at the same time is perpendicular to the rotor as well, rotor surface. Okay, and it happens to all the points. Yeah, yeah? So not only single point, but all the points. Yeah, where the flux lines are leaving the magnetic pole. Okay, and on the other side of the core is the same thing. Yeah, similarly we've got the same effects on here as well. So it's going to go through the shortest distance before then it's entering into the south pole. Okay? And again, this all will be perpendicular to the surface of both rotor and also the surface of the magnetic pole. Okay. Right. So we should remember this. And again, one thing that we need to highlight is that it's perpendicular to the surface. Yeah. This we need to highlight. And we need to understand, and also remember this as because this is going to be one of the things that we need to know when we want to understand how the motor or the generator works later on. Yeah. Okay, I hope it's clear enough. There's no questions up to this point.
No, sir. Oh, good.
Okay, good. I hope it's the same for everyone. Okay, now, okay, the first thing after that is we want to look at the voltage inductions. Yeah. Okay, there are two effects that we want to see. First is a voltage induction, and then the second is torque induction. Yeah. Volt induction, again, this will help us to understand how a generator works, while the other one, the torque induction, is going to help us to understand how a motor works. Yeah. Right, but your understanding in the voltage induction will also help you later on. It will be easier for us to understand the induction of torque because there are a lot of similarities in there. Right, if the rotor is rotated, a voltage will be induced in the wire. Okay, this is we are referring to the same rotor and same loop as we saw on the previous slide. Yeah. So meaning that remember that the loop is not locating randomly, but it's actually located between two magnetic poles. Yeah. So you've got magnetic poles, and then if you remember in our previous lesson, when you've got a piece of wire, yeah, you've got a piece of wire, and then your wire is located inside a magnetic field. Yeah, this is B, magnetic field, and then your wire is moved, yeah, cutting across the lines of the magnetic field. Then remember that voltage will be induced in the in the wires. Yeah, so you got, then if you close the loop somehow, then current will flow. Okay, I'm not sure about the direction. You can check with this going to be right hand rule. Yeah, Fleming's right hand rule to determine but I'm just drawing this for illustration. Yeah, okay, to refresh our mind what we learned in the previous lesson. Yeah, so this is what was happening when this piece of wire is moved across this magnetic field. Then voltage will be induced. Okay, so similarly now you've got the coil here, the wire. Yeah, remember this is okay, different color maybe. This is the wire. To stick. Okay, there's a piece of wire. Not only one actually. You've got a few of them. They're connected together, obviously. There's one on each side, and then you've got one here as well. And then you have this as well. Yeah. Okay, and then it's going to be connected to the external world through these lines here. Right. And now you rotate the rotor. When you rotate the rotor, then this will be all these wires will be moving as well. Yeah. So the wires or the segment, each segment will have some velocity relative to the magnetic field. Yeah, because the magnetic field is stationary. Yeah, it's not rotating, but you've got the rotor moving inside it, and the loop will also move or rotate with the rotor. Okay, so there will be V. There will be V, yeah, which is velocity, and then you've got B, the magnetic flux, and then you got L. So yeah, L is the length of each of the segment. Now, depending on whether they have an appropriate angle or not, then you will get the induced voltage if the angle is correct. Yeah, I mean, you've got some because it has then to have to follow this equation, that the induced voltage is equal to V cross B in brackets times dot L, yeah? The product L. L is again length of the wire, or the each segment in this case, right? So I'm saying that it has to have the right angles, yeah. If V cross B, for example, if they are parallel, then V cross B will be 0, and therefore there is no induced voltage. Yeah. So we need to make sure that there is some angle, for example, between V and B. Yeah? They are not in parallel, i.e. the angle is not 0. Okay, and also the vector product of V and B is not perpendicular to L. If they are perpendicular to L, then also the induced voltage will be 0, or there is no induced voltage. Okay, right. Now we are going to look at what we want to do now is to calculate, yeah, to calculate how much voltage will be induced around this loop. Yeah. Okay, so this is what we want to achieve now. We want to be able to calculate what is the induced voltage generated, yeah, around this loop. Okay, so this is what we are going to do now. Okay, I think I've lost something. Okay, it's not. There's no mathematical equation, but it's stated here in the sentence. Yeah, the total voltage. Yeah, if you look at this, the total voltage can be determined by sum of all the resulting voltages in its segment A, B, C, D, B, C, and D, A. Yeah. What does it mean? It means that if you want to calculate what is the voltage that is induced around the loop, that what we need to do is to find the voltage induced on each segment. So this is what color is better? This is okay. No. Take care of this. Right. So AB, yeah, this VAB, and then second one is different color, BC, yeah, and then CD. Okay, and finally DA. We just assume it to be one segment. Yeah. Okay, so the total voltage, yeah, will be simply VAB plus VBC plus and so on until you get the last one which is VDA. Okay, I hope you can see it. You can read my handwriting. Yeah, the total voltage is VAB plus VBC plus VCD actually, and then plus VDA. Yeah, all the 4 segments. Okay, so now we want to calculate one by one, and after we know each of these voltages, then we can find the total voltage. Yeah, just simply by summing all of this up. Okay, now that's what we are going to do. We start with the segment AB. Okay, we are going to start with segment AB. Where is AB? Okay, this is AB. Right, and then if you on the right hand side here, illustration, this is the front view. So AB is actually at the back, yeah, behind the what they call the rotor. Yeah. Okay. Oh, sorry. No, AB is this one here on the right hand side. So it goes from the front to the back side, yeah? On the right hand side. Okay. So how much voltage going to be induced? Right. So first segment AB, V is tangential to the path of rotation. Right. This illustration here, remember that, okay, we are assuming it to be rotating counterclockwise. It's rotating in this direction, yeah, the rotor. I mean, we are referring to this part here. Yeah? This is the rotor inside. Yeah, it's rotating counterclockwise. Okay. And then, this is the segment that we are talking about currently. Just going to be like a dot, yeah, from the front. When we look at it from the front side, then it just looks like a dot, yeah, this wire. And so this is rotating counterclockwise, which means that the linear velocity, yeah, is actually going in this direction here. Okay, and this is going to be our vector VAB. Okay, the velocity of that segment, the velocity of the wire moving across the magnetic field. Yeah? Okay, how about the direction of B, the magnetic field at that point? Can anyone guess or describe where is in which direction is B in that point? It's maybe a bit difficult to answer, yeah, especially to describe it. Okay, but what we need to remember is what we discussed in the previous 3 slides, I think. Yeah, this one here. So we need to refer to this. Yeah? That the magnetic flux is leaving. Yeah, is leaving. Is leaving the core perpendicularly to the surface. Perpendicular to the surface. That is the answer to that question. So this is the direction of the magnetic flux, which is perpendicular to the surface of the rotor. Yeah. Okay. So you got the V, and then you've got the B, and L is perpendicular to the surface of this page. Yeah? Right. So now, can we calculate what is the induced voltage on that segment by using the equation that induced voltage is equals to V cross B dot L. Yeah. Okay, V cross B dot L, because V, what is the angle between V and B in this case?
90 degree.
Yes, correct. It's 90 degree. Yeah. They are perpendicular to each other. So V cross B is the angle is 90 degrees. So what is the magnitude of V cross B? Oops. The magnitude of V cross B is V times B. This is, I'm talking now about the magnitude, yeah, not the vector. Sine. What is the? I think we use theta. I think for this, yeah. Okay, let's just use theta. And theta is 90 degree. What is sine 90 degree? Sine 90 degree is 0 or 1?
1.
1, yeah. So we are just left with simply V times B. I should write more clearly. Okay. Okay. V dot B, and then or multiply. This is actually multiplication here, and times L, which is the length. So this is the magnitude of V cross B. Yeah, and V cross B, if you use this method, V is, if you use your right hand side, V pointing that direction, and then B, yeah. So the direction of V cross B is following the thumb, yeah, which is into the page, and which means that they are going in the same direction as L, and therefore the angle between the two is 0. So V cross B is parallel to L, and therefore the magnitude is just simply VBL. Yeah? The magnitude of the voltage that is induced, yeah, is simply VBL. Okay, and it's positive into page. You can use the right hand rule to determine the direction of the current. Yeah. Can we try it? Can we verify the right hand rule? Because remember, induction of voltage we use right hand rule. Yeah, and then for the force, induction of force, we use the left hand rule. Okay, so for the right hand rule, we use FBI, yeah? FBI, F, and then in this case we change it into V. So V is up, and then B is like this. Or you cannot see the screen, so and I will be into the page. Yeah? You can see that if you use the follow the illustration on the screen, V and B, and then match it with your fingers appropriately, then you will find that I will be into the page. Okay, so the EBA is positive into page. Yeah. IE, if you look at this, then this will be positive, this will be negative, but the current will be flowing this direction. Okay, if it's a closed loop. Okay, so we got the answer. Yeah, again the answer for the first segment AB. Now the second segment BC. Yeah, we've done this one. Okay, sorry. Before let's finish this one first. There are two conditions. Yeah, I forgot to mention. There are two conditions here. Yeah, the voltage induced on that segment AB depends also on the position. Yeah? On the position. Yeah, on the position of the rotor. Yeah? Let me delete all these scribbles first. Yeah, you've got different results depending on the position of the rotor. I.e., the segment will have different induced voltage if it is here compared to when it is there. Yeah. Imagine if the what we call the rotor rotates. Now VAB is on the top position. Yeah. Then different voltage will be induced. Yeah. Actually, at that point, the induced voltage will be 0 on that segment. Why? Okay, it depends because of the direction of the vectors. Yeah, at this point, V will be in this direction. That's V, and then B is also in the same is parallel, although it's pointing towards the other direction. If you like, at this point, B will be in this direction. Remember, between the poles, it's not perpendicular, because it's not going anywhere, but it's going horizontally. So the angle between the two is 180 degrees, and this will give the V cross B equals to 0. Yeah, and therefore the induced voltage at this point will be 0. Yeah? Okay, the positions like this we call it under the pole. Yeah, because this is the pole. We call it under the pole, while if it is in this kind of position, we call it between the poles or beyond the pole edges. Between the poles or beyond the pole edges. Okay. So there are two values that you get for this segment. Actually, there will be more. There will be more. Yeah. Now, if I again remove all this, if, for example, segment BA is within this region here, so within this region here, the values will keep changing. Yeah? So between the maximum, which is VBL and 0, yeah? So there will be some transition. Yeah? As it rotates counterclockwise from maximum, it's going gradually, yeah, gradually to 0. Okay. Right. We'll see the plot later on, but basically, we can simplify. We can just assume that there are two values for VBA depending on the position of the segment, is either VBL or 0. Right. Okay. So this the first segment done. Now segment BC, and segment BC is the segment behind the rotor. Yeah. It's behind the rotor. So in this position, if you like, if I draw it again. It's not this, right? Okay, at the back, the segment will be like this, yeah. Yeah. So this is that's B and C. But this, imagine this is at the back, not at the front side of the rotor, behind the rotor. Yeah? Okay. In this case, yeah, the induced voltage will be 0. How do you explain that? The easiest is if you look at what is the velocity, what is the relative velocity of this piece of wire relative to the magnetic flux. Yeah. And you will see that the answer will be 0. Why? Because each of this point, yeah, will have different velocity. If you take a few points along the wires, each of this will have a different velocity. If I draw it, the vector, this is just oh, it's too thick. Sorry. Oops. That's the wire. Okay. Let me see. If I draw it one by one, I hope you can see it on the screen. This is just rough. The vector will be like this. As long as you go further away from the center, the velocity will be bigger and bigger. Yeah, it's get larger and larger. On the other side, it's going like this. Yeah. Why? Because it's remember the velocity is what we call the angular velocity times r. Yeah. R is the distance between the center point to the respective points. Yeah? Okay, and because the distance is getting larger and larger, and therefore the speed, the velocity is getting larger as you move away from the center. Okay, now if you look at this, then what is the average? What is the total velocity here? If you take the integral of this, what is going to be the velocity, total velocity? You should find that the velocity will be equals to, the effective velocity will be equals to 0, yeah? Because they are all of the same magnitudes on the left-hand side and the right-hand side, but they are going in the opposite directions. Yeah? So the total speed will be 0, and therefore there is no relative speed, yeah, velocity of the wire relative to the magnetic field, and therefore that's why the V cross B will be equals to 0, and therefore you don't have any induction or induced voltage in this case. Okay. Right. Okay. So and then that's for segment BC, which is the segment at the back of the rotor. for the segment in the front of the rotor, you'll get the same answer actually, yeah, for the same explanation. And therefore, for segment DA, yeah, this DA, which is the segment at the front side, yeah, of the rotor, you'll get zero induced voltage as well. Okay, so 3 segments are done: AB, BC, and DA. The one on the right, at the back, and in the front. Now the one segment left, which is the segment on the left-hand side, yeah, which is segment CD. Okay, and the good thing, segment CD is very much similar to segment AB. Yeah. So this is segment CD, and we already calculate segment AB. So we just follow the same steps, yeah, as we derive or work out the value of induced voltage on segment AB. But now you just need to adjust the directions of the vectors. Yeah. For example, if you remember, for the segment AB, the B was pointing this way. Yeah. But for segment CD, which is on the opposite position diametrically, the B is into, yeah. Oh, yeah, okay, the B is into. So which is actually the same direction in this case. Yeah, the B is in this same direction actually. What the V? Okay, the V will be different. Yeah, the V for this for segment AB, it was pointing this way, but now it's pointing this direction. Okay, so this is B and this is V, and L is still the same, and that's why now the induced voltage will have the same magnitude but different or the opposite polarity. Yeah, if you refer back to this, the positive and negative, if you notice, they are in the opposite direction. It's because now the V is not in the same direction but in the opposite direction to the previous V. Yeah. Okay. So now we've got all the values for the induced voltage for all the segments. Now we are ready to calculate the total induced voltage around the loop, yeah, which is the sum of all these voltages. Okay. Right. Okay. So what is the total? The total will be again the sum of all of each of the induced voltages, and you should get this answer here, yeah. Because the EBA was VBL, DC was 0, EDC was VBL as well, and plus 0. So you end up with 2 VBL. Okay, watch out. This is these two are end up in the same direction. Yeah, if you look at here, minus positive and minus positive, just like if you imagine, this is just going to be like a battery. You got two batteries, you connect them in series, yeah? And the way you connect it is like this now. Positive, negative, positive, negative. You connect the positive side of one of this into the negative, yeah? So the total will be 2 times the voltage of its battery. That's exactly what we've got here, 2 times VVL. Yeah? If, for example, somehow you got the opposite result here, yeah, instead of negative, positive like this, you got this here positive and this one is negative, then the total voltage will be 0. So there is no induced voltage around the loop. But fortunately, what we got is the other one. It's not like that. Yeah. So the total will be 2 VBL. If there's no voltage induced, total is 0, then our generator will not gonna work. Yeah. It's not gonna work. Right. Okay. So and then as the rotor rotating continuously, what will you get then? Yeah. So what you will get is this. this will be the induced voltage around the loop that you will get. Okay, it's going to be basically, if you simplify this, it will keep changing from 2 VBL to 0, and then it goes to negative. Yeah, after the rotor rotates by 180 degrees, yeah, this is rotating by after 180 degrees, you get the opposite output. Yeah, and then goes to minus 2 VBL, then go back to 0 and positive and so on. So if you simplify, this is just like a pulse waveform. Okay, but yes, obviously there is a transition period here where it actually gradually changing. It's not a sharp change, but it's a gradually changes. Yeah. Okay. So any questions so far?
Oh, sir.
Okay. Okay. What's this? Okay. Sure. Anybody else? Any question? You can write down in the. Either you can speak it up or you can write it on the chat box. Cannot see where's the chat box. Currently, I cannot see the chat box. If any of you has written on the chat box, please let me know. Okay, why I cannot see it? Okay. Anyway, okay. Let me know if you have any question. Yeah? Right. So this is what we get so far. Now we want to develop it. Yeah, we want to develop basically this equation into a more generic form. Okay. And this is why we've got this also. What is it? Okay, this one here. Okay, we already derived that the induced voltage is equal to VBL. Yeah. Okay. Now we want to transform this, if you like, into a different form, different equation, so that it gets or becomes more meaningful. Okay, we know this. V is equal to R times omega, where omega is angular velocity of the rotor. Yeah, we know that. And then we also know this. Flux is the multiplication of the magnetic flux density and the surface area. Yeah. Okay, the tricky bit is that A is equals to pi RL, half of the cylinder. Right. The flux that we are talking about here is the amount of flux that's going into the rotor. Yeah, that is going into the rotor, which is also going to be the same as the flux leaving the rotor. Okay, so how much flux is entering the rotor? Yeah, we use this equation that the flux is equals to B times A. And the B is the magnetic flux density coming from the magnetic pole, and A is the cross-section area. Okay, now the tricky bit is how do you find the value of A? To know the value of A, it's actually not complex, but we need to know what it is. Yeah? The assumption that we use, remember that we have a cylindrical core. Yeah, it's 3D. The magnetic flux entering the core on one side, yeah, if you like, and leaving the core on the other side. So in this calculation, to simplify the problem, we assume it to be that it's entering into half of the cylinder, yeah? And it's leaving from the other half of the cylinder. So what we need to find is for this cross-section area is the area of half of the cylinder. Yeah. So this half here. Yeah, I hope still makes sense to you. But yeah, you can imagine a cylinder and just half of it. So the cross-section area of the half of the cylinder. Yeah? So half of the cylinder maybe looks like this. Okay, something like that. So we want to know what is the this area, right? So how do you find the area? The area will be the length of this half of a circle, the length of this times the depth. In this case, the depth here we use the value of L, right? The length of the wire, the segment. This is L. How about finding the length of this? This is the perimeter of half of the circle. Yeah? If you have a circle, what is the perimeter of the equation for the perimeter of the circle? Assuming the radius is R, the perimeter, what is it? Anyone want to try?
Pi R.
Pi R. Pi R. Is it correct? Pi R.
Pi R.
For half, yeah? For a whole circle, if you have a complete circle, what is the perimeter?
Pi R.
2 pi r, sir.
2 pi R, yes, correct. Yes. So for a full circle, that will be 2 pi R. But if you have only half, then it's 2 pi R over 2, which is pi R. Yeah. So the cross-section area for this half of the cylinder will be I equals to pi R times L, yeah, the length. Okay. So this is where this comes from. Yeah. Okay, so again, you need to know what is the assumption. The assumption that is entering into half of the cylinder, yeah, and that's why the area that we need to find is the area of half of the cylinder, yeah? Just the side, yeah? not the front and the back sides. Okay, so that's where the pi r come from. Okay, now we've got all the equations, and then apart from these three, we also have this equation, yeah, the one that we got from the previous that we derived previously. So now, if you then use these four equations, then you should be able to convert this equation here, the top one. Well, actually, it starts from the one here, from this, yeah. The one that I draw on the top, yeah, on the right hand side, yeah. Yeah, because you cannot see where my pen is here. Yeah. You should be able to derive or to convert this equation into this. Okay. How do you do it? Okay, let's try it. How do you do it? The easiest way. 2r omega. Okay, so the first thing is you change or replace v with r omega. Yeah. So 2vbl, you substitute v with r omega, and you will get this. Yeah. 2r omega bl. Yeah. Only replacing v with r omega. Okay, that's first step. Next step, what has been done here? These two are the same. It's just a matter of restructuring it, yeah, reordering it. So you move the omega to the back. Yeah? Everything else stays the same. Right, now from this to this, what have been done here? B omega stays the same. Yeah? B omega stays the same, but RL has been replaced with A over pi. RL has been replaced by A over pi. Why? This is actually coming from the A equals to pi RL. Yeah. Okay, so you replace RL by A over pi. So you get this equation, and finally A times B is pi. Yeah, watch out the pi. Pi here means what we call the torque, yeah, the symbol for the torque. And the rest is the same, 2 over pi times torque times omega, which is speed, angular speed. So this is the final form of the equation. Okay, and why is it important to get it into this form? Because of the explanation shown in the box below. Okay, and this is will be a similar later on when we look at the for loop and the more realistic machine. The equation will be of the same or similar form as what you see here. Induced voltage is equal to 2 over pi times the flux. Sorry, did I say torque? Yeah, it's supposed to be flux. Yeah? This is not torque, but this is flux. Sorry, 2 over pi times flux times omega m, angular speed. Yeah? So what is can read from the box. In general, the voltage generated in the machine depends on the flux in the machine. Yeah, and then the speed of rotation omega, and finally a constant representing the mechanical construction of the machine. In this case, is 2 over pi. 2 over pi applies when we have a single loop. When we have a for loop, this 2 over pi will change. When we have a real machine, this 2 over pi will change again. But the flux in omega m stay the same. Yeah. Okay. So and this is why we call this the constant representing the machine design. If you are designing as a single loop, a for loop, 8 loop, and so on, this value will change, yeah, depending on your design. Okay, but the omega and the torque and the flux will stay the same. Will stay in the equation. Yeah. So in this voltage depends on a constant, depending representing the design, the flux in the machine. Yeah, it means that the higher the flux you have in the machine, the stronger or the higher the magnetic the induced voltage. Yeah, which is good when we're talking about generator. And that's why how do you get the high flux? By using a ferromagnetic core. Yeah, if you don't have the ferromagnetic core, your flux will be low. And it also depends on omega m. Yeah, on omega m, the angular speed of rotation. Yeah, if you're talking about wind turbine, it means the faster it rotates. Yeah, i.e. it depends on the wind. Yeah, if you've got strong wind, it will rotate faster, then your generator's voltage will be higher as well, generally speaking. Okay, so these three factors are the important factors when we talk about induction of voltage in a generator. Right. Okay. Wow, it's already 1 hour already, nearly, just for the single loop. Okay, any question? Are you silent? You're confused or you understand? Or you're sleeping? Yeah, I cannot see your faces, so it's not like in the real class. Yeah. Right. Okay. I assume that you all understand. Yeah. Let me know. Well, you can also type later on in the WhatsApp if you have more questions. Yeah, further questions. Okay. And here, what do you have? Here we got right. Getting DC voltage out of the rotating loop. Okay. Remember that the output so far that we got is not a DC. Yeah? The output is alternating positive and negative voltage, which is this here. So it's an AC actually, the output. So how do we get a DC output from this? Then we need to use this mechanism called commutation. Remember commutation. So it's a very basic fundamental stuff that we need to understand when we talk about DC machines. Commutation. Okay. So what is this commutation mechanism? So you've got first these two semicircular conducting segments called commutator segments. Yeah, these segments here. You got two of them. Each of the segments is connected to the end of the loop. Yeah, remember the loop has got two ends. Each of the ends of the loop is connected to one commutator segment. Okay, and then you've got two fixed contacts, which called the brush. Yeah, the brush are this, and they are making contact to the segments, the commutator segments. And by having these two, then we will have the output to be having a single polarity rather than two. Yeah? The output now here. Yeah, this is the output of the machine. Before, when we didn't have the commutation, the output was at the ends. Yeah, at the ends of the loop, which are this. Yeah? Hope you can see. Yeah. So this was the old one, the old connection. Yeah, and then this is the new one with the commutation. Okay, so the output at the old terminals, if you like, or the ends of the loop, they are alternating positive and negative. Yeah? But here it's already converted, or rectified. It becomes more like what you can see on the plot down here. Yeah. So now the output is like this instead of this. Before it was going positive, negative, positive, negative. Yeah, it's now all the negative side will be converted into positive. If you follow this, why? Because now every 100 after 180 degrees, yeah, the connections between the loops and the brushes, yeah, through the brushes will be inverted. Yeah, the connection every 180 degrees rotation, it will be converted, and that's why now the output has got always the same polarity. Yeah. Okay, I hope you can imagine it. Yeah. Remember that, yeah, okay, watch out as well that the segment here, the segments, commutator segments follow the rotation of the rotor. Yeah, as the rotor rotates, the loops is rotating as well, and the segments follow as well. But the brushes are fixed. Yeah, they are not rotating; they are in the fixed positions, and that's why every 180 degrees, the connection between the commutator segment and the brush will change. Yeah. So, for example, if your segment is A and B, yeah, and then you've got the brush. Let's call the brush C and D. After 180 degrees of rotation, this will be B. Segment B will be there, connected to C, yeah, and segment A will be connected to brush D. Yeah, remember, only the segments rotate. The brushes are not rotated; they are fixed. Yeah, and you can see initially A and C are connected, B and D are connected. After 180 degrees is B and C, A and D. So the opposite. Yeah, and that's why then you have this effect here. The negative will be converted into positive, yeah, into the opposite polarity. Yeah. Okay, so from this, can you work out what is the function of commutation? Why do we need the commutation? Anyone can voluntarily answer that question? Let me see this, if I can see the screen. Or maybe I should say a name. Brother Muhammad Anas, so what is the function of the commutation?
I'm not sure, sir.
You're not sure? Okay, next one. Next, who can I? Brother Hafizuddin?
Maybe rectify the voltage signal.
Yes, okay, that's correct. Yeah. So to rectify, yeah? Which means that by using the commutation, our output will be of the always of the same polarity. It's not having the alternating polarities anymore. Yeah, i.e. is converting from AC to DC. Yeah. However, be careful in answering a question as well, because commutation is doing both ways. Yeah, it's converting from AC to DC when we are talking about generators. But when this applies to motors, it's the other way around. It's going to be the other way around. The output is AC. Sorry, the output is DC coming from a battery or something, and the commutation actually will then convert it into AC. Yeah. That will be applied to the rotor, and therefore the rotor can rotate properly. Okay. Right. So, okay, I think, yeah, this is another illustration of commutator and brushes. Maybe more clear here. You can see this is commutator, and again, commutator rotating with the rotor. These two brushes are fixed in position. Yeah, and normally you've got springs. These brushes are spring loaded. The idea is, as is aging, yeah, as the motor is aging or the generator is aging, the brushes getting worn out, yeah, because of the friction. So bit by bit, this will get worn out. Will become shorter and shorter, and the springs are making sure that the brush always push towards the commutator segments. So they are always make contact. Yeah. If there is no spring, you can imagine it's already removed, then it will be loose. Yeah. And it might lose the contact, or the contact will be intermittent. Sometimes it's making contact, sometimes it doesn't. Yeah? But this is the function of the spring, and this is actually the weakness. Yeah, the weakness of DC machines, because why? Because of these brushes. These brushes, because of the friction. Yeah, every time the rotor rotates, there's friction between the brush and the commutator segments, and the friction will remove, yeah, bit by bit the part of the brushes, and the brushes will get shorter and shorter until eventually it will stop working. And this becomes the weakness of DC machines. Then, because when this already worn out so much, then you need to replace the brushes. And if you want to make sure that it's always functioning whenever you need the motor, then it means it needs regular maintenance. After some number of hours that it has been running, then you need to replace the brushes, just like maybe replacing the oil for your car engine. Yeah, that you need to change regularly. Yeah? Otherwise the motor will, or the generator will stop working. And again, you can highlight this. This is one of the weaknesses of DC machines. Yeah? Okay, it's all 35. Yeah, we still have 15 minutes. Okay, let's see if we can now go through the second part, yeah, which is the induced torque in the rotating loop. Okay, maybe for this one, I will not go in so many details. Yeah, but the concept or the principle is very similar. Yeah, it's just now, instead of induced voltage equals to V cross B dot L. Yeah? Now the equation is now induced force equals to I times in bracket L cross B. Yeah? Okay. So yeah, later on when the derivation, I will not go in too much details. Okay, now but the significant difference now, if you look at, we are still talking about the same loop. Yeah? Still talking about the same loop, but now we have the commutation. yeah, the brushes and the segments. And also now we have battery, yeah, or voltage supply. Yeah, you can say battery or a voltage supply, which can be connected or disconnected by using this switch. Okay. Before we didn't have this. Now we have all this battery. Yeah, and the R is the resistor represents the resistance or the resistances around this all this path. Yeah? The path means that if I can draw it, it will be current can flow like this. Yeah, from the battery through the brush segment and then to the loop. Yeah, going around the loop, and then current will come back to the battery again. Yeah, from the terminal side. Okay, now so this is the idea. So now if you look at the loop, now you have current flowing. Yeah, current flowing, and then for segment AB, for example, current flowing out of the page. In segment DA is into the page. Yeah, and segments AD and BC is on the line. Yeah, if you like, of the rotor ends. So this that we'll need to consider when we derive the value of f later on. Yeah, yeah, because watch out of because we have a vector operation here. You need to work out the directions of each of these variable, yeah, or vector I, L, and B. Okay, so again, the way we derive it is still the same, yeah, just like before. But now we just using this equation. So and then the value that we need to look at is the I and its direction. L is stay the same like before, and B is the same as before. Yeah. So what you will find that for segment AB, yeah, you've got this. The torque will be equals to this. Yeah, so you've got some value, and if AB is between the poles, then the value will be 0 again. Yeah, so and again, I'm not going to details. You can follow just like how we went through step by step last time. Okay, so to cut it short, then this is the value that you will get. Yeah, the total. Okay, the torque. Yeah, because the total torque. How do you find the torque? First, from the calculation, we calculate forces first. Yeah. Sorry, F is give you ILB, then you can convert it into torque by multiplying with R, yeah, R sine theta. Okay, and then you can find the total torque by adding up them up together. But for segment CD and AB, sorry, AB, something was not right here. You got AB, C, where's BC? This is BC. And then CD and DA. Yes, okay, this is the wrong one. Okay, for the segments at the front and the back side of the rotor will be 0. So this will be 0. This two will be 0. And these two got values, which is RILB. Yeah, R because we multiply ILB with R to make it into torque. Yeah, torque is again R times F. Basically, yeah, if they are perpendicular. Okay, and then again by using, remember how did we get this pi RL for the A, and then we got this equation as well. So from this, then you should be able to derive this, yeah, which is very similar. Yeah, previously we've got this. Yeah. So in this voltage was 2 over pi, which is a constant, times the torque times the angular speed. Now for torque, 2 over pi stays the same, which is the constant, and the flux is still there, but now we've got I instead of speed. Yeah? We've got current instead of speed. Yeah? Okay, so in exam, this question comes again and again. What are the three factors that determine the value of induced torque? What is the values of what are the three factors in determine the value of induced voltage? Yeah? So this is the answer. So for induced torque, it depends on the flux, the current, and the constant representing the mechanical construction of the machine. Yeah, because the 2/pi will change when you have the for loop. When you have a real machine, this constant will change, but the flux and I or current will stay the same. Yeah? Will stay in the equation just like this. Okay, and from this also we need to highlight that torque, yeah, because you will play with motor so much. Torque depends on current. Again, yeah, torque depends on current, not voltage. Yeah? So be careful. You apply high voltage, not it doesn't always mean that it will have higher torque. Yeah? It will depend on the situation, what the load, etc. But it always depends on the current. The higher the current, the higher the voltage. The higher the current, the higher the torque. Yeah. Similarly, with this one, induced voltage, it depends on the speed. Okay, which later for motor, it means that induced voltage is just like voltage. Yeah. For motor, if you want a motor to run faster, it means that the voltage across the motor has to be high. Yeah? The higher the voltage, the faster. The higher the current, the higher the torque. Yeah? So these two are the V relates to the speed, and current relates to the torque. Yeah? Okay, this is a very important concept that we need to understand and also remember. Right. Okay. Right. I think the question, can we go through the question example? I think it's a bit too long. We'll leave it till the next class, I think. Okay. Yeah, okay. I think that's all I think for today. I think that's enough, more than enough for you. Especially you've got this synchronous class, maybe not as convenient as our normal class. Yeah, even 1 hour and a bit already too long actually for synchronous class. But I hope you can follow it, and in case you want to rewatch it, you can do so later on, inshallah. I will share the link to the video as well, inshallah. Okay, before we close this class, anyone's got any question or comment?
So sir, the voltage, induced voltage is for generator and induced torque is for motor, right?
Correct. Yes, correct. However, it actually applies for both. When we talk about motor, there is actually induced voltage as well in the motor, but we are not talking induced voltage as being the output of the motor. The output of the motor is torque. Yeah. When let's talk about motor. Let's assume that we're talking about motor now, and the rotor rotates. Yeah? As the rotor rotates, actually voltage then will be induced as well in the rotor, just like when you have a generator. Yeah? And this voltage that is induced, its polarity will be the opposite to the polarity of the voltage of the battery. Yeah? So when later we will discuss this a bit more later when we discuss about some examples. We will see this. So when a motor actually running stationary, yeah, it's running stationary. Sorry, not stationary, at a fixed or constant speed. Yeah. So you've got a motor. Let's say you've got small DC motor. You connect it to a battery, then it will run. Yeah? Start rotating and until it reaches a steady state speed. At that voltage, if you measure actually across the what you call that you connect to the motor, and then if you then measure the current, there's no current flowing anymore. Why? Because there's a balance now. The voltage of the motor is the same as the voltage of the battery, and therefore but of the opposite polarity, and therefore there's no current will be flowing. Yeah, there's no current will be flowing. If I can quickly, okay, let's say you've got battery, and then you've got motor. Yeah. Okay. This motor will generate induced voltage at steady state speed. This voltage of the battery will then, or if you, I should say that the induced voltage will be the same as the voltage of the battery. Okay. And therefore, there's no current will be flowing. So current will be zero. Current is zero means that the torque is zero. So when it's running at constant speed, the motor doesn't have any torque anymore. And that's why when there's no torque, there is no acceleration, no deceleration, right? And that's why it's running at steady state speed. The speed is constant. When there is no force, there's no torque, speed is constant. Yeah. That's when the equilibrium is happening. Yeah, the voltages of the two are the same. So yes, actually similarly when we talk about generator, actually some torque also introduced in there, and that's why when the generator has to generate very high current, yeah, the torque will be, the torsional lock will be high, and it means that the wind has to be, if we're talking about wind turbine, the wind has to be stronger to generate to be able to generate the current that we need. Okay, maybe you're still confused, but later we will some examples. I hope when we go through the examples, it will be more clear. But for now, yes, at the output, when we talk about motor, the main output that we concern about is the torque, but induced voltage is also there. It's happening. Similarly, when we talk about generator, the main output that we want is the voltage, but they call it contra torque. Contra torque is also happening, yeah, inside the generator. Okay.
Yes, sir.
All right. Yes, it could be a bit confusing for now, but I hope when we go through the examples later on, you can get better understanding as well. All right. Any other question? That's a very good question, by the way. Yes, thanks. Any other question? Okay. Right. If there is no more question, that's I think that's enough for now. Yeah, for today. And we can finish now. And let's recite Suratul Asr and Tasbih Kifarah to close our session today.